In this video, we are going to be finishing up the concepts of Chapter 8. The first thing that we're going to explore is combined gas laws. Combined gas law is where we are combining the three previous laws that we talked about: Boyle's, Charles, and Gay-Lussac's law. And as you can see, in combined gas law, we have all three properties in one equation, which state that initial pressure multiplied by initial volume divided by initial temperature is going to equal to final pressure, final volume divided by final temperature. Okay? Now, in order for combined gas law to be true, N is constant. And remember that N is going to be the number of moles for a gas. Okay? I always want to say that combined gas law is going to be the most useful equation. That's why it is present in the exam reference sheet. And it's because combined gas law can be utilized to derive all three equations. Okay, so make sure that you know how to derive the equations based on combined gas law, and it is going to be done in the following manner. So remember, for Boyle's law, because you're looking at pressure and volume, because temperature is constant, if you say, okay, my temperature is constant, oh, there you go. I have the equation for Boyle's law. When it comes to Charles' law, because pressure and number of moles is constant, it's kind of like you're blocking the pressure. And then there you have Charles' law. And lastly, for Gay-Lussac's law, because for there we have the number of moles and the volume constant. It's kind of like you say, okay, the volume is constant. And as you can see, that's how you can derive Gay-Lussac's law. Let's actually do a problem on combined gas law. As you can see, the problem states a gas has a volume of 675 milliliters at 35 degrees Celsius and 646 millimeters of mercury of pressure. What is the volume in milliliters of the gas at negative 95 degrees Celsius and a pressure of 802 millimeters of mercury? Remember that for this problem, your number of moles for a gas is constant. Well, as we have done in the other problems, the first thing that we're going to do is write our equation, which is P1 times V1 over T1 is going to equal P2 times V2 over T2. Okay, so as you can see here, we are looking for the new volume. So we're trying to solve for V2. When we rearrange this equation, okay, we know that V2 is going to equal P1 times V1 times T2. Everything divided by T1 times P2. Okay? All we did is that on both sides, we multiplied them by T2 over P2. That's how we solve for it. Make sure that you practice your algebra. Now let's state the values given. So as you can see, here we have our V1. Here we have our T1. Here we have our P1. Here we have our T2. Here we have our P2. Now, similar to what we saw in Charles' law and Gay-Lussac's law, understand that specifically we need to change those temperatures to degrees Kelvin. So this is another instance which temperature must be converted 2 Kelvin units. Okay, so to do this, we're going to do 35 plus 273. So that means that this is 308 Kelvin. And then when we do negative 95 plus 273, that is going to be specifically 178 Kelvin. Now we're set up to do the problem. So in order to do this, we're going to write in the values. So P1 is 646 millimeters of mercury. We're going to multiply that times P1, which is 675 milliliters. And we're going to multiply that times T2, which is 178 Kelvin. We're going to divide the whole thing by T1, which is 308 Kelvin. And that value is going to be multiplied times P2, which is 802 millimeters of mercury. As you can see, the millimeters of mercury cancel, the Kelvin cancel. And our result is going to be in milliliters, which is what's the unit requested. So we're going to do 646 times 675 times 178, and we're going to divide that by the multiplication of 308 times 802. So we get here that the final value, if we round it to 3 sig figs, is going to be 314 milliliters. The last gas law that we need to be familiar with is going to be Avogadros Law. And this Avogadros Law was created by the guy that invented Avogadros number. Remember that he was interested in the number of moles. So when it comes to Avogadros Law, understand that this is the equation, is the relationship between volume and the number of moles. That means that N, which is the number of moles, is proportional to volume. So when this happens, understand that as one increases, the other one also increases, okay? They're directly proportional to one another. Remember that for Avogadros Law, in order to be true, we are going to have temperature and pressure constant. Let's do a problem on Avogadros Law. So as you can see, here the problem states, if 0.75 moles of helium occupy a volume of 1.5 liters, what is the volume in liters? If we now have, or the problem reads, will 1.2 moles of helium occupied at the same temperature and pressure? Okay, so when it comes to the equation, let's write it down, which is V1 over N1 equals V2 over N2. We are trying to solve for volume, which is V2. So we rearrange our equation. V2 equals V1 times N2, everything divided by N1. And then again, in this problem, remember, you need to convert, not for the problem specifically, because it's already a number of moles, but make sure the amount of gas is in moles. Okay, in this problem we don't have to convert it, but make sure that in the future you are doing an Avogadros Law problem, you need to change it to moles before you get started. But for this particular problem, as you can see, we have our V1, we have our N1, we have our N2, and then we plug in our numbers. 1.5 liters multiply by 1.2 moles divided by 0.75 moles. The number of moles cancel. Then we do 1.5 times 1.2 divided by 0.75 equals 2.4 liters. So the volume that will be occupied by 1.2 moles is going to be 2.4 liters. And that's how we do Avogadros Law.